everybody gets this. So in ALEKS, you see the SLO assignment, and you will also find that in Blackboard under the weekly lessons for this week, week 14. So here's the write-up for it. It just freaks me out every time I do it. There we go. So here's the SLO assignment. So what we have is called Student Learning Outcomes. And what we're doing is we're taking our goal, our QEP, and making sure that our students we're seeing student learning outcomes in our classes. So what we have is one assignment that's each class has one, and it's the one assignment that's shared across all Math 171s. I also have a 143 class. All 143 classes have a different SLO assignment. So what this covers is Chapter 2. There may be some content from Chapter R and Chapter 1, but the main content or the main purpose of this is the Chapter 2 material. So this is, if we were face-to-face, I would actually do this on paper and time you. But since we're online, I can't do that. But I need you to act or to be like a class that meets face-to-face. So what I've done is I've added this assignment. It looks like a test in ALEKS, but it is not. It's going to be a lab grade instead. But I've got it set up in ALEKS as a test. You have 45 minutes to complete it. It's 4 questions. And understand that I'm not going to be grading, or when we sit down to grade this, faculty from outside of our department are going to be grading it. So they're going to be looking for completion and understanding, which means writing and showing your work, explaining what you're doing or why you're doing it. So you'll need to submit this. So this is due the same day as the test, next Tuesday, the 22nd. And when you submit it, it's got in there, you need within 10 minutes of completing the assignment in ALEKS, I need you to submit the SLO assignment, or the whatever you've done on paper. I need you to submit that in Blackboard as well. I would recommend doing this assignment as prep for the test. So I'd get the SLO assignment out of the way at some point between now and the 22nd. And then maybe I could spell Chapter 2 right on the test. Oops. So yeah, so that's up. You'll get an email. You get an email and an announcement from me noting these 2 things. Just like before, Chapter 2 test is up and available. We're going to finish 2.5 today. I'm going to take any questions, and if we have time, we'll get into 3. If we don't have time, you'll see a video for 3 pop up. Oh, you don't? Oh, okay. Test. Oh, I've got it opening at 5. Here, let's fix that. Let's open it now. At 12 a.m. All right. Test has been shortened. It was 14 questions. Now it's 12 because I wanted to remove some of the material that I did not want to show, didn't want to show up on the test. So you get 12 questions, 2 hours. I believe I've extended the time for everyone that gets an extension. If I have not, please check your time before you start the test. So when you click on the test, you'll get the pop-up. Oh, dang it. You'll get the pop-up screen, and it'll tell you how much time you have allotted. If I've not done it for you yet, please email me. But I believe I've got everybody's done. All right. That is okay, Chloe, no problem. We were just discussing, you're going to see an SLO assignment, which is just like, it's really just it's more of section 2.5 mainly. And what graphing rational functions looks like, what does it mean? what causes horizontal asymptotes, what causes vertical asymptotes, and explain. So you'll do the assignment in ALEKS and work. You're going to work to write. You're going to do all your work out on paper, submit the ALEKS assignment, and then take pictures using. No, you do not need a webcam. So do your CamScan app, submit the single PDF just like normal, and the submission is under the week 14, under weekly lessons. So week 14, and this is where you submit. I'm going to change the order here. This is where you submit the SLO assignment and the Chapter 2 test work. And then all that's due by the end of the day next Tuesday. And then that way, Thanksgiving is, we're going to try to get into 3. We'll definitely be in Chapter 3 on Tuesday. So this way we can stop, enjoy, celebrate Thanksgiving, and then just make that mad dash to the end of the semester. That is the time between Thanksgiving and the Christmas break and the end of the semester. It's always a bit of a rush, but I think we're actually going to have we're going to have more time than I thought we would. We've got a lot to cover after Thanksgiving, but a lot of it can be done quickly and with more videos. After this, no, just one. So this test, and then there's a test. So what's left is Chapter 3, and then there are 3 sections from Chapter 8 that we will cover. The way I see this working now, does it work for the SLO? Yes, it does. Yes, so any work completed for the SLO needs to be submitted in that, submitted as a PDF, just like the work has been for the tests each time. Okay, and my other classes, I was pretty lenient with submitting your work on the test, and on this last test, it's changed. If you do not submit work with your test, it's 20 points off. Your test gets dropped 20 points. I've got them. You know, we're coming up here on the last 2 tests, so I'm very serious. I need to be able to see the work you're doing. You're in an online. I know it's a synchronous online, but I still can't monitor you and I still can't proctor you. I'm glad that you get to have the extra time that I'm allowed to give you because we're online or outside of class, and it makes it where our lectures I don't have to lose a day for a test, but I still need to see. It's not enough just to show me the right answers. It's show me the right answers and show me how you got the right answers. I'm really much more interested in you understanding the material than I am about you being able to find the vertical asymptote of a rational function. It's more of the process or the procedure than it is about can you find that. All right, so SLO assignment test is SLO assignment is open in ALEKS. Test is open in ALEKS, and you got 5 days, which should be plenty. We're going to do the last 4 pages of the 2-5 notes. If you printed the notes from the PDFs, the first 4 pages of the part 2 2.5 notes, the first 3 pages are repeats. So the first page or the 4th page of that 2.5 rational functions graphing and applications file, it's the page that starts out with these 4 steps. That's the first page that's not a repeat. This was originally one big file and we split it into 2. But when we split it into 2, we copied 4 pages into both of them by accident. So sorry about that, but that's why it looks like I'm just taking a big jump if you've printed the notes out, because this is where we start. So we're gonna sketch. We got 4 graphs or 4 rational functions to sketch, 2 application problems to do, and then we'll see where we are. We'll see if there are any questions outlying or outstanding, and then we'll go from there. Anything before we dive into 2.5? No? All right. So how do I sketch a rational function? If I want you to graph a rational function, I'll tell you to go graph it on Desmos. I want you to sketch a rational function. I want you to be able to get the idea, get a good idea of what the function looks like, not so much nail every point spot on. So what we are told to do is find all asymptotes and holes, okay? Determine where there's any places that we cross horizontal asymptote, locate the intercepts, and then find a point in each section and use the asymptotes to guide your curve. So that last part we're going to talk more about, and I'm going to show you how to break down. I'm going to take a number line and kind of break it down into where it says each section. So let's start out at the beginning, because a good beginning is a great place to start. Part one, find all asymptotes and holes. All right, so does this f of x equals 3x plus 6 over x minus 2. The numerator does have, both terms have a 3 factor of 3. So I can factor out that 3. And I have 3 times x plus 2 over x minus 2. It looks like there's something you can do there, but there's not. Okay, it that top factors, but you cannot divide x plus 2 and x minus 2. Right? Think about it. If x is nothing, you have 2 in the numerator and negative 2 in the denominator. You cannot divide those. Now you're thinking, oh, that's 2 and negative 2. I could just, it'll be the difference of a 1 of a sign. No, because as soon as I change x to 3, now you have 5 and 3 are your numbers. You can't divide those and get anything out of it. So as tempting as it is, because it has the same first term and second term, you cannot do anything with it. So asymptotes occur when the denominator is 0 and that factor is not matching. Well, we don't have any matching factors here, so I know right off the bat there will be no holes in this graph. I know I'm going to have a vertical asymptote when the denominator is 0. When you see me write this vertical asymptote, x minus 2 equals 0, and then you see this arrow, this is me, instead of continuing to write below to take up more space on the paper, this is me just jumping over and just saying, in essence, doing that instead of, so don't think this is x minus 2 equals 0 equals x equals 2. It's not that meant to be that confusing. That arrow there is to help us. All right, so vertical asymptote at 2. So let's go do that. Here's my vertical asymptote at x equals 2. Okay, so step 1 done. Vertical asymptotes, all asymptotes. Oh no, vertical asymptotes are found. I haven't found the horizontal ones yet. Okay, horizontal asymptote. Well, the numerator is degree 1. The denominator is degree 1. When the numerator and the denominator have the same power, the horizontal asymptote is the ratio of the leading coefficients. Leading coefficient for the numerator is 3. Leading coefficient for the denominator is 1. So I'm looking at y equals 3. So there is the horizontal asymptote. Okay. Now we said I'd mentioned just before that we have sections. Okay. Well, vertical asymptotes divide up my graph into its sections. Okay. So I have a section that's to the left of x is 2, and I have a section to the right of x is 2. So let's see if we can find any more points. And if we do, then we really don't have to worry about finding points in all the sections. So that's part one, done. Part two says to find anywhere, find a point or points where the graph intersects the horizontal asymptote. Remember, we can intersect the horizontal asymptote all day long, and that is fine. So I want to know, when will my function give me the horizontal asymptote's y value? Horizontal asymptote's y value is 3. So solve. Okay. Everybody's favorite operation, which is not really an operation, cross multiplication. I end up that if these two fractions are equal, these two, this rational function is equal to this ratio, then 3x plus 6 times 1 must be the same thing as 3 times x minus 2. 3x plus 6 is equal to 3x minus 6. Get x by itself, right? So subtract 3x from both sides. And now I have 6 is equal to negative 6. That is false, correct? 6 does not equal negative 6. So when I do math, all my variables fall out. That means I'm going to end up in a situation where either this function is always true, or excuse me, this equation is always true, or this equation is never true. When I get something back that is false, and what I mean is all the x's go away and I end up with something that's false, that means 3x plus 6 over x minus 2 is never equal to 3, which means that I do not cross the horizontal asymptote. Does that make sense? Okay, so there's never a time where I cross the horizontal asymptote here. All right, step 3 is to locate the intercepts, y-intercept and x-intercepts. So let's go for that y-intercept. Yes, absolutely, it can cross horizontal asymptote. If you end up with x equals 4 or something like that, it will cross it at 4. Then you'll have to find the y value by taking your whatever you find your x value to be, plugging it into your function and see it. It can cross horizontal, it can never cross the vertical. So y-intercepts occur when x is 0. So literally just plug 0 into my function and see what I get. 0 minus 2. 3 times 0 is 0. 0 plus 6 is 6. 0 minus 2 is negative 2. So it's negative 3. So that means I've got the point 0, negative 3. 0, negative 3 is here. And where's my x-intercept? X-intercepts happen when y is 0. So that means I need to take my function, set it equal to 0, and solve. Now, same process as before. I have a rational equation, but instead of like over here in step 2, notice I have a rational expression is equal to 0. There is no way that the denominator can impact this answer. Now, I tell you what, how about we just make it easy and do the same exact procedure we did before. So I'm going to show you what's going to happen. I still have my ratios on both sides. I got the rational expression and ratio over here. If two fractions are equal, then that means their cross products must be equal. So that means 3x plus 6 times 1 must equal x minus 2 times 0. See how that cross multiplies? So on the right, x minus 2 times 0 is just 0. So I end up with 3x plus 6 equals 0, which means 3x is negative 6, which means x is negative 2. So I end up with the point negative 2, 0. Where is negative 2, 0? It's right here. Okay, so I have 2 points. They're both in the same section though, all right? Step 4, find a point in each section and then use the asymptotes to guide you. I've got a couple points over here to the left. So what is my function going to do? It's going to hug the asymptotes. So as x heads off toward negative infinity, as x goes to the left, as my function goes to the left, this is going to get up here and hug that horizontal asymptote. As x gets closer and closer to 2, guess what the function does? It hugs that vertical asymptote, y equals 2. All right, so that's part of my function. That's one section, but I need a point with x greater than 2 so that I know where this goes, right? Because this rational function or this rational graph, it could be down here or it can be up here. Okay, I don't know which one it is. So the last step, I need to find out, I need to get some points for what about when x is 3, 4, 5, 6, 7. I can do any numbers that I want to. Let's look at our original equation and try to make our lives easy. So remember, this is f of x is equal to 3x plus 6 over x minus 2. So if I can pick any numbers I want to that are greater than 2, I'm going to pick numbers that are going to be helpful or that are going to come out nice. Right off the bat, look at the denominator. If I pick something, well, denominator doesn't really do anything for me, but imagine here if there's a case where maybe if you plug in 3, you get a nasty answer, but if you plug in 4, you get a much nicer one. Take a look at that. This one doesn't really do anything. Both of everything I do, I'm pretty much going to end up with a fraction, but that's okay. So let's try 3 and see what happens. Plug in 3. 3 times 3 is 9, plus 6 is 15 over 1, which is 15. So when I plug in 3, I am way up here. Okay, so that was a little off the graph. So let's go a little bit farther to the right. Let's try 4. Plug in 4. 3 times 4 plus 6 over 4 minus 2. 3 times 4 is 12 plus 6 is 18. 18 cut in half is 9. Do I go up to 9? Nope, I go up to 7. So 8, 9, somewhere in there. So I'm way up there. So let's keep going. Let's try 5. Three times 5 plus 6 over 5 minus 2. 3 times 5 is 15, plus 6 is 21. 21 divided by 3 is 7. That's on the graph. So at 5, 7, there's my first point on the graph. And then I can keep moving to the right. Looks like, 6 or 7. Let's try 7. 3 times 7 plus 6 over 7 minus 2. 3 times 7 is 21. 21 plus 6 is 27. 7 minus 2 is 5. So this is what I meant by my fraction's not pretty, but I can use it. 27 over 5 is 5 2/5, right? 5 goes into 27 5 times with a remainder of 2. So when x is 7, I'm over 5 but under 6. It's 5 2/5. So right there. Okay. Now, once I have a couple of these, and really as you do more and more of these with examples, you're going to figure out that, look at that behavior, even though those points aren't on the graph. What am I doing? I'm doing the same thing I'm doing over there. I'm hugging both of those asymptotes. And this is what my graph looks like. Okay. The nice thing about taking math in this year or in this time is you can always just plug this into Desmos and see if you get that sketch. Can you cross? You're just reflecting over the asymptotes. Yeah, that's what it looks like. Yeah, it looks like I folded it up and then folded it to the right. The reason that I'm up here, so I want you to take a look at the original function here. When x is to the left of 2, okay, and this is gonna kind of take, you have to zoom out a little bit with me here. So when x is less than 2, okay, and so what happens up here? When x is less than 2, this could be positive or negative. When x is less than 2, this is always negative, right? 1 minus 2 is -1. So this thing's always negative in the denominator when I am to the left of 2. This is always negative. This is negative when x is to the left of -2 and positive when it is to the right. So this is why my function, you can see, is x gets more and more negative. I have a negative over a negative, which results in a positive y value. Okay? When x goes to the right of -2, what happens? When I go to the right of -2, the numerator becomes positive all the time. The denominator stays negative, so positive divided by negative is a negative. And you see how I dive down toward negative infinity? Now, what happens on the other side of +2? Well, if I'm larger than 2 and I plug those numbers in, the numerator is always going to be positive. The denominator is always going to be positive. I'm talking like just over 2, like 2.1, 2.01, right? Doesn't matter. As long as it's over 2, this is always positive. This is always positive. A positive divided by a positive is a positive. And look at where I do. I'm up here. As I move to the right, as x gets larger and larger, it doesn't matter how big x gets. This is always positive. This is always positive. Look at where the graph is. Do I ever go negative down here or in this to the right of 2? Absolutely not, because I'm held by that horizontal asymptote. Okay, so that's why in this problem you've got your you got the graph down there for x's to the left of 2, and then you see that reflection across it's not really across the origin, it's across those asymptotes, and you see it hanging out up there in the top right. There are cases where instead of hanging out up here, this could be down here, and this can be up here. So that's why we have to check. That's why we do those points, we do those test points in each section, just to make sure that we know, am I above the vertical horizontal asymptote? Am I below it? And then have I done the other stuff right? Okay, so a lot of information, I know, but it will all come together with more examples. Okay, so next, g of x is equal to 4 over x squared minus 9. Just like rotating. Yeah, it is. Yeah, Andrew, you're right. I didn't see your last comment there, but you're absolutely right. It looks like I've rotated around just not around the origin, but around some point right there in the middle there. So next one, steps, okay? Holes and asymptotes first. This is difference of perfect squares in the denominator. So yes, that factors into x plus 3 times x minus 3. All right. Does the difference between leading coefficient being positive, being negative, change which quadrant the graph is in? Yes. Yes, it does. If the leading coefficient, so in the problem above, if this had been negative 3x plus 2, both of these would get flipped. So my graph to the right of 2 would be down here. My graph to the left would be up here. In this problem, no. And in this problem, and that's because, or the sign of the variable does not impact where the graph lives, because when I plug in a number for x, I immediately square it. So even though I plug in positive numbers and negative numbers, the result of that, of then plugging it in and squaring it, always comes out positive. So you're going to see this one act a little bit different. Okay. So once again, no holes because no shared factors, but I do have vertical asymptotes, and those live at when x plus 3 is 0, which occurs when x is negative 3, and when x minus 3 is 0, which is happening when x is 3. Okay, so at negative 3, I tried to learn my lesson. On drawing, it's just easier to sketch these than it is to try to make a vertical line go dead on. That is negative 3, and then there's another one over here at positive 3. So vertical asymptote at 3. Okay. So vertical asymptote done. Horizontal asymptote. Leading coefficient. Let's see, what have I got? Sorry, degree. Degree of the numerator is 0 here. Degree of the denominator is 2. Whenever the degree of the denominator is greater than that of the numerator, that horizontal asymptote lives at y equals 0, which is just the x-axis. Okay. I just kind of noticed that in the previous problem, all of this was blue. So we'll make sure that works out later. Okay. So vertical asymptote's done, horizontal asymptote's done, no holes exist. So let's keep moving. Next step, part 2 of my procedure. Determine any points where I cross the horizontal asymptote. Okay, so take my original equation. Over x minus 9, and I set it equal to my horizontal asymptote. My horizontal asymptote is 0. I'm going to run into the exact same thing I did before. If I write that as, set this up to be cross multiplication, what I'm going to end up with is 4 equals 0, which is false. So once again, no cross of the horizontal asymptote. The shorthand of this procedure is what you'll find out as you do more and more of these. When you have ignore the rational part for a second. When you have a fraction equal to 0, you cannot divide your way to 0. There's no number you can plug in down here because there's no number divided by that you can take 4 and divide it by to get out 0. So what you end up doing is you essentially just get to ignore the denominator for this part and say, when is 4 over x squared minus 9 equal to 0? When 4 is 0. Is 4 over 0? No. So no cross of the horizontal asymptote on this one either. Okay, next step, intercepts. Okay, so that's step 2, that's step 1. Step 3 was the intercepts. So let's go after that y-intercept first, which means I'm going to let x be 0. So what do I have? 4 over 0 squared minus 9. 0 squared is 0, 0 minus 9 is negative 9. So I'm looking at the point 0, negative 4/9. There's one asymptote, or excuse me, not one asymptote, one intercept. And let's go under that to get the x. X-intercept means I let y be 0. So my original function equals 0. I already found that to result in 4 equal to 0, which is false. So that means that there's no x-intercept. Right? It just so happened that the horizontal asymptote is 0. And so when I get down here to do to find the x-intercept by letting y be 0, I end up with the same result. I never cross horizontal asymptote, and I never have an x-intercept. Well, take a look at the graph and think about that. If I never cross the horizontal asymptote of y equals 0, then I can never cross, I'll never have an x-intercept. Does that make sense? Both those things have to be true, right? If it never crosses horizontal asymptote, I never have an x-intercept. If I don't have an x-intercept, I can never cross the horizontal asymptote. So it makes sense that those two things would carry over. So I got the point 0, negative 4/9. So 0, negative 4/9 is going to be somewhere in here. And now I've got some issues, right? I have 3 sections that I need to fill. I have 1 point. Okay, so I'm going to need to fill in for x less than negative 3. I need some between negative 3 and 3 because all I have is this single point. I'd like to have some other values in here. And then I need to look at when x is greater than 3. All right, so I'm going to take some numbers less than negative 3, plug them into the original, and see what I get. So did you notice last time that if I'm really close to these vertical asymptotes, you remember last time how that y value was off the chart immediately? So because of that, instead of picking negative 4, let's pick negative 5 or negative 6 or negative 7, because when I get really close to this vertical asymptote, I'm either going to be diving for negative infinity or for positive infinity. Every time you run into one of these things, you're either diving toward positive or negative, just depending on where you are. So instead of picking the number right beside my vertical asymptote, I'm going to try out, what was my letter for this? G. Let's try out negative 5. Exactly, Andrew. Yes, it gets really steep because I never touch that asymptote. I want to, okay? The function is dying to touch the asymptote. It just can't. So what happens when I plug in negative 5? I end up with 4 over, and then, yep, and that's going to start happening because now I'm going to start hugging that horizontal asymptote. Negative 5 squared is 25. 25 minus 9 is 16. 4 over 16, which is 1/4. So g at -5 is 1/4. G at -5 is 1/4. Where is that? That is just above this horizontal asymptote, but it is above it. All right. Since I know this point, here's my section over here to the left of -3. I know my point is up here. So with just one point, it's not recommended, but with just that one point, I can start drawing, right? I know I live up here, and I know that I'm sketching, not trying to nail this exactly, right? So since I'm up here, my sketch is going to look like what? I'm going to hug that vertical asymptote. I'm going to hug that horizontal asymptote. What about down here in between? Well, somebody tell me what you think this is going to do. If I'm getting, when x is 0, I'm at -4/9, what's going to happen? Well, I can't cross the vertical asymptotes. I never cross the horizontal asymptotes. So if I'm going to just hug asymptotes, well, then this is going to hug and come down. This is going to hug and come down. So there's that sketch. So I've got both of those regions covered. How about when x is greater than 3? Well, let's try it. So when x is greater than 3, I'm going to do the same thing I did before and close the window for some reason. What in the world? Okay. When x is greater than 3, let's come out here to 5 and see what happens. So g at 5. It's going to do the same thing as the other one did. Right? G at 5 is 4 over, now I just have 5 squared minus 9, which is 25 minus 9, which is 16. So g of 5 is also 1/4. Where does that live? Right up here. So if I know that point lives above the horizontal asymptote, guess what the function's doing? It's doing that same behavior. It's hugging the vertical asymptote as x gets closer and closer to 3, and it's hugging the y, the horizontal asymptote, as x gets larger and larger and larger. Okay? And then, like I said, you have so much technology that it's almost offensive for someone that came up before this. Does that match up with the actual graph? Yep. Okay. Now, what's the difference in this graph and what we did on the sketch? Well, on the sketch, there are points. So if you pull up the graph of Desmos and then you say, oh, this is my sketch, you don't have the x-intercepts labeled. You don't have the y-intercept labeled. You don't have the horizontal asymptote labeled. You don't have the vertical asymptote labeled. So sketching and graphing are different things. Please understand that when I ask you to do something, or when I'm asking you to do these sketches, really I'm after you. I want you to show me that you know. Yeah. Oh. What I want you to show me is I know how to find vertical asymptotes. I know how to find holes. I know how to find a horizontal asymptote. I know how to find any place that I cross the horizontal asymptote. I know how to find intercepts. And then I know how to find points when I run out of, or when I don't have enough information to finish my drawing. Okay? And again, this is not, that obviously is not a function because it doesn't pass vertical line test, but that's just the idea of the sketch here. All right. So let's sketch a couple more and then see what happens. Next, I have h of x is equal to 3x squared minus x minus 4, all divided by x plus 2. So does this factor, can I reduce this? Yeah. And I need to do that because I'm not finding the domain first. I'm finding vertical asymptotes and holes. The difference in a vertical asymptote and a hole is, right now it looks like x plus 2 is the denominator. It looks like I have a vertical asymptote, but x is -2. I do have a vertical asymptote at x is -2, as long as the numerator doesn't have a factor of x plus 2. Because if the numerator and denominator have the same factor, that's not a vertical asymptote anymore. Now it's a whole. All right, so 3x squared minus x minus 4. How does that work? Oh, my poor watch thinks it's time to stand up. It's like you don't even know what my job is. All right, so does this factor? Yes. I need to multiply to 3x. So the only way to do that is 3x and x. And this is guess and check. I'm not doing the bottoms up method, but you can. But I do know these two have to multiply to 3x. I know that the second two, the constant terms, have to multiply to -4. So that's either -4 and 1, 4 and -1, 2 and -2. And then I just have to be careful that the inner and the outer come out to -1. So think through this one with me for a second. 3x times x is 3x squared. So if I can do 3x times 1 and x times -4, don't I end up with -4x plus 3x? Does that match up? Does multiplying these two result in 3x squared minus x minus 4? Let's find out. 3x times 3 is, ooh, no, that's 9. And then what happened here? -4 times 3 is 12. Oh, I did it wrong. Okay, so let's try it again. 3x and x is right. And I only do this when that leading coefficient is prime, right? The only way to get 3x squared is 3x times x. So again, I need to multiply to 4, but I want to be careful. I don't want that 4 to have anything to do with that 3. So if I put it here, -4 plus 1, does that do it? 3x times x is 3x squared. 3x times 1 is 3x. -4 times x is -4x. -4 times +1 is -4. Yes, it does. So we nailed it. Do any of these match? No, no factors are shared. So again, there's no holes. But I do have vertical asymptote when I got ahead of myself. I was so excited to draw the arrow that I forgot to do math. When x is -2. Okay, how about the horizontal? Come back to the original. Numerator has a degree of 2. Denominator has a degree of 1. When that happens, there's no horizontal asymptote, but there is of anybody remember the word? Slant. All right, how do I find that slant asymptote? I do the math, I do the division. So I need to do this division. I can actually do it with synthetic really easily. So 3x squared minus x minus 4 divided by x plus 2. So in the box goes the value that makes the denominator 0. So that's -2. Coefficients are 3, -1, and -4. We drop the 3, and then we're off to the races. 3 times -2 is -6. -1 plus -6 is -7. -2 times -7 is +14. -4 plus 14 is 10. So that tells me what? This was a quadratic or second degree polynomial. I divided it by a first degree polynomial. So that means my slant asymptote is 3x minus 7. Where is that graphed? Okay, well that's a line. So when x is 0, y is -7. So I start here, and I'm just going to find another value that works out nicely here. When x is 3, 3 times 3 is 9, minus 7 is 2. So when x is 3, y is 2. What happens when x is 1? When x is 1, 1 times 3 is 3. 3 minus 7 is -4. 1, -4. There's my line. Okay. So there's my asymptote. Ooh, that looks more like a hurricane than an asymptote. So let's go through these points like we're supposed to. Up we go. This is not a solid line. It is because you saw when I graphed this, it actually doesn't show up on the graph, but the behavior is, the behavior shows up on the graph pretty strongly. All right. 1, -4, 3, 2. Yeah, okay. So there's my slant asymptote. Next thing, do I ever cross the horizontal asymptote? I don't have one. I don't have a horizontal asymptote, so I don't have to check for that. So no horizontal asymptote, no check for crossing. Next thing, that was step 2. Step 3, intercepts. Find the y-intercept by letting x be 0. If x is 0, take a look at this really quick with me. If x is 0, everything that has an x goes to 0, right? So that's 0 minus 0 minus 4 over 0 plus 2, which is -4 divided by 2, which is -2. So 0, -2 is my y-intercept. Okay, how about my x-intercept? Let y be 0 and find out. So that means I have 3x squared minus x minus 4, all divided by x plus 2 equals 0. Now I'm going to jump 2 things here. Remember, I said you can't divide your way to 0. So when is this rational expression equal to 0? Only when the numerator is equal to 0. If you want to do the cross multiplication, you'll end up with the exact same result. You'll find that 0 times x plus 2 is 0. 3x squared minus x minus 4 times 1 is 3x squared minus x minus 4. We already factored this earlier into 3x minus 4 and x plus 1. Solve. Move your graph. Because I know if I know one thing, I know I didn't leave you enough space to do all this writing. 2 things multiply to give me 0, which means one of them is 0. So 3x minus 4 is 0. 3x is 4. X is 4/3. X plus 1 is 0. X is -1. So that means I've got x-intercepts at 4/3, 0, and -1, 0. 4/3, 0 is right here. 4/3, 0, and -1, 0. Okay. So I got that. What else? So this one's a bit odd because of that slant asymptote cutting through it. So next thing I want to do is I don't have any points to the right of the slant asymptote, right? So I do want to try to find something over here. I'd also like to find something over here because this isn't really, this is very confusing, right? It looks like a triangle. Something I didn't do though is I didn't graph that vertical asymptote that we found. That's going to help a lot. Right, so x is -2. So I can't cross this. My slant asymptote is taking care of, really, it's just the end behavior, because that's what horizontal or slant asymptotes do. So I need to be to the left of -2, and I need some more values over here to the right so that I can get an idea of what this graph is supposed to look like. Okay, so let's find some more points. So let's try out -4, see what happens. And then we're gonna do some math in our heads real quick. -4 squared is 16. Minus -4 is +4 over -4 plus 2. That's a 48. That's not going to be on the graph, is it? 48 plus 4 minus 4 is 48. -4 plus 2 is -2. So that's -24. So where am I at least? I'm at -4. I'm way down here. I actually end up being below that slant asymptote. That's how far. No, I'm not below it, but I am down there. I'm way down here. So does it get better the farther left I move? At this point, if you're finding values, you're more than welcome to, again, use the technology to your advantage since you have access to it. When you go to take this test, you're going to find that I don't have the lockdown browser on because I expect you to use Desmos. I expect you to use things that you would not normally have access to. All right, so let's just do what I said. There's h of x. It's hard to see it, but that's what it looks like. So use this to our advantage. Let's see, what was it when I got to -5? I'm at -25 1/3. What happens when I go to -8? Does it get better? No, I'm still way down here. So how about to the right? So what about h at 4? Can I graph that? Yeah, I can graph that. What about h at 8? No, I'm going all over the place. So with those extra points included, and the graph is just not to scale very well, what does this thing look like? It's gonna hug this asymptote, it's gonna come down, and it's gonna run off to that slant. And then when I get down below, my vertical asymptote and my slant asymptote are going to cross. And then when they do that, I'm going to see this same kind of behavior going up and down from here. All right. So I know somebody popped a question up right in the middle of that. And I'm sure it was a response to what I just said out loud. But let me make sure. Yeah. So yes, you can use Desmos on this test because Desmos is not going to actually feed you the answer that I'm looking for. It may give you some points on a graph like this, but it's not going to tell you the answer, because if you draw this or you sketch this in your answer, then you're going to need to be able to find vertical asymptote, horizontal asymptote, y-intercept, x-intercept, because those are things you're going to find algebraically. So yes, Desmos, you're going to be wide open on the test. Pretty much open note. Sure. Yeah, you can Photoshop however you want to. Absolutely. So yeah, so this test, and like I said, I'm still gonna send an email out just to remind everybody what the rules are. You know, the test is going to be that you're not going to have the lockdown browser engaged, you're not going to have the webcam engaged, so you're not going to have any issues. You're going to be able to use the internet, use Excel, you don't use Excel, it's my other class, use Desmos, and yeah, just use whatever tools and features you need to help you, but also understand that just like the last test, I'm going to be, if I ask you to do this sketch or you get a question like this, I want to see this work, not just a perfect drawing of this is what the graph looks like. All right, does that make sense? You can see how, and you can also see how there's only 12 questions on the test. In this one question, we've covered 2.1, 2.2, and 2.3, and the first part of 2.5, right? Because we talked about vertical asymptotes, we talked about holes, we talked about slant asymptotes, we talked about intercepts. All that stuff came from 2.1, 2.2, and 2.3. So a good question in 2.5 answers tells me, do you understand 2.1, 2.2, and 2.3? Now I'm going to skip the last one because it's a hot mess. Not that that one was pretty by any means. And let's go after one of these application problems. I'll finish these notes in a video, post them into the YouTube channel, so you'll see all the application problems and that last sketching problem done too. I have a rational function that describes the cost in thousands of dollars to remove X% of air pollutants for a coal power plant. All right, so first question, compute the cost to remove 25% of the air pollutants. X is in percent, so that means just take 25, plug it in for X. So that's 600 times 25 over 100 minus 25. 600 times 25 divided by 100 minus 75 is 200. Okay, what does that mean? That means it's going to cost $200,000 to remove 25% of air pollutants. Okay. Now, this is going to work. Here's the problem, though. We tend to think that if it costs $200,000 to do 25% of it, our brains work in a linear fashion. So $200,000 to do 25%, well, that means with $400,000, I can do half of them, and with $800,000, I can probably remove them all. That's great if your function is linear, but this is not linear. It's rational. So what's going to happen as the percent go up? Well, because X is messing with the numerator and the denominator, this is not going to work in a linear fashion. So to get half, that's not a dollar sign yet, to get 50% of the pollutants out is going to cost me $600,000, right? The relationship is not linear. And why is that? Okay. It's the same reason that the oil industry in the US seems to have fallen off a cliff. It's because we got a lot of the easy oil to get. Like, remember, we were energy independent. We got a lot of the easy to reach oil that was right underground. Okay. Well, okay, great. Well, where's the rest of the oil? Well, the rest of the oil is going to be harder to get to. Just like it's easy, I say in quotations, it's easy to remove 25% of the air pollutants. It's the rest of it that's hard, right? And the more I want to remove, the more it's going to cost. Same thing with oil, right? If I want to pump more oil, a lot of the easy to reach oil has already been gotten. So now it's going to cost more to pump more oil. So now I've gone from 50 to 75%, and now I'm at, so that's $1,800,000. which is 1.8 million, right? Because remember, these are in thousands of dollars. So now to remove 75%, it's going to cost me 1.8. What's it going to cost me to do 90%? That is going to cost me $400,000. 5,400,000 to remove 90%. See how that rational function is annoying, but it works? This is a real, this behavior is common in the real world. Just like we were saying, if the oil is really close to the ground and easy to dig, that's easy to get out of the ground. If the air pollutants are large particles and all I gotta do is throw a filter over it to get them, that's easy. Okay, well now I want you to remove 50% of the pollutants. Well, I've got all the easy stuff out of the way in that first 25%. So now the particles are smaller. So now my mesh or now my filter has to be finer. So now it's going to cost me more, right? And then you want 75% of the pollutants out of the air. Well, now just a filter is not going to do it. Now I may have to do some kind of chemical process to take all the, to take out everything that goes out the smokestack and then run it through some chemical process where I bond the carbon to maybe, I say that like I'm a chemistry teacher. I may want to bond the carbon or get the CO2. Maybe I want to sequester the CO2 underground. Okay, that's going to cost more. And it's not just going to cost a little bit more. Getting that last bit out, getting those last few percent out is costing. Look at how quickly that cost curve rises. Okay. Now, what if I go the other direction? If a power company budgets 1.4 million for pollution control, what percentage of air pollutants can be removed? Okay, so that means one good 1.4 million corresponds to C of X being 1,400. Everybody cool with that switch? And I know we're getting close to time. If you need to go, I'll finish the problem and then I'll post it. But if you do need to go, I understand. So set this up. So what is C of X? C of X is the equation. And the equation is 600X over 100 minus X. Thanks, you 210 equals 1,400. All right. Cross multiply, because that's what everybody loves to do. And I'm going to end up with 600X times 1 is equal to 1,400 times 100 minus X. Distribute on the right. 1,400 times 100 is 140,000. 1,400 times negative X is 1,400X. This is linear, right? Highest degree of X is 1. Everything with X to one side, everything without to the other. So if I add 1,400X to both sides, all the X's end up on the left. And all the non-X's end up on the right. Now, while X completely by itself, it's currently multiplied by 2,000, so I'm going to divide both sides by 2,000. And I find out that X equals 70. So that means 70% of air pollutants can be removed for $1.4 million. All right. And then the last question here is, what is the domain in the context of the situation? So let's remember, scroll it for a second. Yes. Is that far enough, Andrew? Oh, for part B. Okay. All right. Tell you what, let me steal. Okay, yeah. Yeah, 75% was 1.8 million. So 70% can be taken out for 1.4. Yeah, that's great that you saw that, okay, that this number was going to have to be less than 1.8 million, right? Because this was less than 75% of the air pollutants to be removed. Okay. All right. So I can get 70% out for that. And then the last question is, what's the domain for this problem? Yes, you should always make sure the math adds up. That is something to live by. All right, 600x over 100 minus x. Now, for this function, for the function c of x, this cost function, if I actually wanted to find the domain of this algebraic equation or algebraic function, I would do what? Does x live under an even root? Does x live in the denominator? There's no roots, but x is in the denominator. So I need to take the denominator, set it equals 0, solve, that gets tossed out. So what's my domain? Everything but 100, right? 100 causes division by 0, so everything but 100 is great. However, for this question, let's come down here and type, okay? If the domain of this function is everything except 100, because that causes division by 0. In the context of the situation, X is the percent of air pollutants we remove from coal factory, the coal-fired power plant. Okay, so X lives between, it's a percentage, so it's got to be between 0 and 100, right? It has to be. So based on the problem, based on that information, the domain should be 0 to 100. And then the question is, do we include the endpoints of 0 and 100? Okay. Do we include 0 and 100? C at 0 is what? 600 times 0 is 0. So that's 0 over 100, which is 0. That's fine. To remove no air pollutants, it costs me nothing. That makes sense, right? To remove 0% of the air pollutants, it costs me nothing. So that one's fine. What about 100? Well, that's going to cause a problem. We already know that from the algebra. When I just deal with this with an algebra sense, that's going to be 60,000 divided by 0, which not allowed to happen. So that means my domain, for the sake or for the context of the problem, it's 0 to 100. I can include 0 because that makes logical sense, but I cannot include 100. Because if I plug in 100, it causes division by 0, which means what for the problem? You really can't. You can't remove everything from, you're not going to be able to remove 100% of the air pollutants. So yes, Andrew, you're absolutely right. You cannot go below 0, right? How much money does it cost to remove negative 10%? That's not a thing. So 0 to 100, because X is a percent, then you go to the algebra, do my endpoints get included? 0 does, 100 does not. All right. Okay, well, we'll call it there. Any questions? I know there's only a few of you left, but that's okay. Anything else?